Hello, my name's Alan Mensinger. I'm a professor in the biology department at the University of Minnesota Duluth, and along with my colleagues Corey Susky and Clark Dennis III at the University of Illinois, we are looking at increasing the effectiveness of big-headed carp deterrence by carbon dioxide integration. And I'm sorry we weren't able to show you our lab in person today, but hopefully this talk will give you a good idea of what we've been doing to stop these invasive fish. So I don't think this audience needs any introduction to the fish that we're working on. We are trying to stop the upstream migration of both the silver carp, which are known for their jumping ability, shown in the upper left-hand corner of the screen, as well as the bighead carp. So these are collectively known as big-headed carp, and they have been migrating up the Mississippi River, and they're threatening Minnesota rivers and lakes, as well as the Great Lakes. So to try to stop the upstream migration of these carp, we have been investigating two methods. One is acoustic deterrence, where carp are presented with a very loud, obnoxious underwater sound, which is actually recording from an outboard boat motor. And as the fish approach the sound, they get deterred by it and swim away. The other option is what is called a bioacoustic fish fence, or BAF. And in this case, it's basically a curtain of bubbles that contains sound, and it has the same effectiveness as the acoustic deterrents. The fish hit the BAF fence, or the bubble fence, and are also repelled. The good news for carp deterrence is that both of these systems have been now employed in the field. So the BAF fence is now operational in Barkley Dam in Kentucky. And if you see on the right part of the photo, you see a little white line, diagonal line going across the picture, and that's the bubble curtain in effect. The other deterrent, which is purely acoustic, it does not use the bubbles, has been recently installed at Lock and Dam 19 in Keokuk, Iowa. The challenges with either one of these options is they're not really a very negative stimulus. They do work in the short term, but we believe eventually the fish will basically get close to the sound or close to the current and notice that, well, we can just plow through these and there won't be any penalty. And so if you think of the advent of a scarecrow, you have crows in your cornfield, you put in a scarecrow, and that works for a limited amount of time, and then the crows realize that the scarecrow is not causing them any harm, and they come back and actually nest on the scarecrow. However, if you add a different stimulus, such as a moving arm or something, now the crows again pay attention to the scarecrow. And so we're trying to develop a system where to increase the effective duration of these acoustic deterrents. One option is to use carbon dioxide in the water. Now, this is a very, very negative deterrent. If the fish do not leave the carbon dioxide area, they will eventually lose equilibrium and die. Fish do not like carbon dioxide. They have both internal and external sensors that are quite sensitive to carbon dioxide, and they will continually move away from carbon dioxide. If they can't move away, they'll go belly up and die, and it's equally effective. However, you don't want to continue to deploy carbon dioxide. It would be very expensive, and it may not be environmentally good. for both the air quality and also other native fishes. So what we've thought is that perhaps we can combine carbon dioxide with sound to increase the effectiveness of both deterrents. And you can see here Lock and Dam 5, and I hope you're realizing a common theme throughout this show is the way to stop these carp from migrating upstream or at these strategic bottlenecks. It is unlikely that the carp will pass through the dams, but they will certainly pass through the lock chambers. And so this provides an opportunity to stop the upstream migration of carp in a relatively limited area where sound and carbon dioxide can work very well. The method we're using is actually just classical conditioning. And if you remember Pavlov's famous dog experiment, he used a bell, which was a neutral stimulus, and food, which was the unconditioned stimulus, to train the dogs to associate the sound of the bell with food reward. And if you just gave the bell, the dog would not do anything. If you gave it food, it would salivate. If you gave it the bell and food, it would salivate. And then after it was trained, if you just did the bell, it would continue to salivate. So the dog had been trained to associate the sound of the bell with food. And so what we like to do here is with the fish, we're going to try to pair sound with CO2. So in the first stage, eventually, and I believe this is true, fish will begin to habituate or just ignore the sound, and they will start going towards it. If we just put CO2 in the lock chamber, they will not ignore it. They will continually swim away from the CO2, and they will never get habituated to it because, as I said before, if the CO2 concentrations get high enough, they basically pass out and they're going to die. So they are going to always swim away from the CO2. And so what we want to do is we want to add CO2 while we're playing the sound. So the fish will associate the onset of the sound always with CO2 release. After conditioning, we believe that if we just play the sound, it will be much more effective. It will be effective for a longer period of time because now the fish will think, we're playing some sound, CO2 is about to come in, we need to get out of this area. So, how is this going to look? Well, again, we're going to target the lock chamber, and we're going to put speakers inside the lock chamber to produce that broadband sound. And then as the lock gates open to allow the upstream traffic to come into the lock, we're also going to add CO2. So we have sound and carbon dioxide paired. And this should hopefully train all the fish in the area that sound equals carbon dioxide. And then in subsequent passes, we're just going to use the sound and see if the sound alone will repel the fish for a longer period of time without the carbon dioxide reinforcement. So, in summary, we want to condition fish to associate high-frequency sound with carbon dioxide. We really think this is going to increase the effectiveness of sound-only deterrents. Also, if we can pair CO2 with sound, we won't need to use the carbon dioxide as much. So this will decrease the use of carbon dioxide and its impact to native fishes and the environment. So what we're doing at MAISRC is to see, one, is this concept going to work in small tanks? And two, what's the magic ratio? How often do we have to reinforce the conditioning with carbon dioxide to make the sound a constant deterrent? So we're having these little shuttle box experiments that we'll show you coming up. Well, this will begin our virtual lab tour. And again, we're sorry you haven't been able to see the lab today, but we are located in the MAISRC Containment Aquatic Facility. So, as I said, we're using these shuttle box experiments, and these are very straightforward. Basically, in one side, we'll be adding carbon dioxide, sound, or both carbon dioxide and sound, and see how long it takes the fish to leave the area and go to the opposite circle, which just contains fresh water. These are two views of our lab, and those white figure 8 containers are the shuttle boxes. Those tall columns allow us to inject carbon dioxide into the water and then add that to the shuttle boxes. And everything is filmed from above as well as monitored by computers that are outside the screen on the far right. This is an overhead view of our shuttle tank. On the left, we see 5 silver carp swimming around, and the left part of the tank is receiving carbon dioxide, or the right part of the tank is just receiving compressed air. And as you can see very quickly, once we start injecting the carbon dioxide, the fish do not like it, and they swim immediately to the opposite side. And these are juvenile carp. However, we have much larger tanks on order that we're going to be looking at the effects of adult carp also. All these experiments are conducted remotely, so we're not disturbing the fish at all. The fish are videotaped from the top, and we have tracking software where we can track the path of the fish. There are other experiments going on with my colleagues from the University of Illinois, and what they are investigating is, if you remember, the bioacoustic fence uses basically air bubbles to stop the movement of carp. They are trying to replace the air bubbles with CO2 to see if adding CO2 to the bath will increase its effectiveness. So they're doing some preliminary experiments at the University of Illinois, and then they will travel to MAISRC to use this large tank that's currently in the MAISRC facility to see if the bath fence is more effective using CO2. Well, thank you for showing interest in our projects. That's me on the left. However, the people that have been doing all the work on the project are shown on the right. And we have Jackie Kulata, who's a graduate student in my lab, Brooke Vetter, who actually did some of the pioneering work on acoustic deterrence in my lab, is now a faculty member at the University of St. Thomas, and she is consulting on the project, and she was kind enough to send us 2 of our undergraduate students this summer. Josh Schropp is also a new student in my lab, and then Eric Chang worked with us this summer from Carleton College. So I'm sorry you weren't able to see the lab. We hope in 2022 we will get you in the lab and also show you all the accomplishments we've made in the past 12 months. So thank you again, and have a good day.